Hi everyone, my name is Loli Martínez, a postdoc at Universidad of Chile, and today I'm going to talk about our project with Super-Eddington AGNs. We can identify a Super-Eddington AGNs throughout the spectroscopic data. So these kind of sources tend to show strong low ionization profiles, but also the profile used to be Lorentzian light profiles. We will not observe really a strong contribution of the forbidden oxygen tree line in the optical, but we will get that these sources are really stronger Fe2 emitters and also stronger Fe3 emitters compared with the general AGN population. And in the high ionization lines will be observed blue asymmetry profiles, which are an indication of outflows, but also an indication of the radiation forces. And usually in the UV, really we are not getting a strong contribution of the helium-2. In the photometric data, also we have observing this result is coming from reverberation mapping and also using other kind of catalogs, that the variability is less than 10%. And here in this diagram, using an independent sample, you will see that there is a negative correlation between amplitude of variability and also of the Eddington ratio. So also photometric data are, if we are getting this kind of values, so probably we can get also identify Super-Eddington AGNs. We know most of this information throughout the Eigenvector 1. The Eigenvector 1 basically organizes the spectral properties of the AGN. If we correlate the width of the H-beta and also the intensity of the Fe2 weighted by the H-beta measured by this parameter known as the RFE, we will get that the AGNs are located in this very well sequence. These AGNs are from the SDSS quasar identified. But AGNs are not located here. So it is an indication that some physical properties are behind this sequence. However, using small samples, we have realized that not only the spectral properties are organized in width sequence. We have realized that black hole mass, ionization parameter, density, and of course the Eddington ratio are also behind this sequence. And apparently all of them are driven by the Eddington ratio plus orientation. So we know this throughout using photometric analysis, and we have identified that the AGNs will be located in this part. As I told you before, the Super-Eddington AGNs will be stronger Fe3 emitters, and they will show a strong contribution of the forbidden oxygen tree. So you will see here that our regions are located here. So basically here. So this is the region where we will try to identify or find the Super-Eddington AGNs. But why is important to understand or to analyze these kind of sources? Well, because recently we have realized that these kind of sources can question some of the classical scenarios of the AGNs or the classical relations that we typically use. One of them is the radius luminosity relation. It is one of the most important results from the reverberation mapping analysis, and as the name indicate, basically there is a relation between the luminosity of the continuum and the size of the VLR. And this relation is very important because if we are able to determine the size of the VLR, we can get an estimation of the black hole mass. And we really don't need to perform a long monitoring such as reverberation mapping does. So we only need to know the luminosity, get the size of the broadline region, and then to get the black hole mass. And this is one of the most typical formulas or scaling relations to estimate the black hole mass. However, 5 years ago, a group was devoted to analyze it, to monitoring these kind of sources. And they realized that the Super-Eddington sources are not really follow the classical radius luminosity relation. They are basically in the below part of this sequence, but also they realized that the departure is related with the Eddington radio intensity, as the color scale indicates here, or the accretion rate. So it's very important to apply a correction and to check what is happened, because if we are using the classical radius luminosity relation or the classical scaling relations to estimate the black hole masses, probably we will get not the correct value. So we can correct the radius luminosity relation by the accretion rate throughout the RFE. That is basically, as I told you before, the intensity of the Fe2 that is derived by the Eddington ratio. So if we perform everything in a multi-component fitting with the size of the broadline region, luminosity, and also the intensity of the Fe2, we will be able to get and to recover the classical radius luminosity relation. And as I told you, it is quite crucial for get a good determination of the black hole mass. This is a classical spectrum from the UV of a Super-Eddington AGN, and in this region we will get some kind of interesting lines that can help us to analyze different parts of the broadline region or the AGN. One of them is the blend of 19,000, where in the Super-Eddington AGNs the aluminum and the silicon tree are dominated the 19,000 blend. In the other kind of sources, basically the blend is dominated by the carbon tree. So it's really important to analyze what these lines are so enhanced in this kind of sources. But also we have the high ionization lines carbon 4 and silicon 4, and here they are useful first to analyze the metallicity, how the metallicity behaves, but also how the radiation forces are influence our AGNs. One of our main ideas or our main proposal to the community is to suggest that the aluminum can be used as a virial estimator. Usually the magnesium 2 is used as the UV virial estimator. This is also a low ionization line. However, when we are in sources larger than redshift 2, we lost the aluminum with the classical ground-based telescope. So that's why we have to look for other one. But usually the people tend to use the carbon 4, but as I told you, it sometimes is stronger affected by outflows or by absorption. So probably it's not the best emission line to get. So that's why we are proposed to use the aluminum 3, that it is a semi-forbidden line, and especially in the Super-Eddington AGNs, it is really very strong. So why not to use this emission line as a virial estimator? And we are observing, we observe the data with also the aluminum and with the H beta, and we will get that they correlate with a relation very close to 1. So you will see here this slope. So this result is give us a strong motivation to really consider the aluminum as a virial estimator. So for this analysis, we are proposed to use the SDSS reverberation mapping. And why we propose to use this sample? Well, basically because since this sample is constantly monitoring, so first we can analyze different properties of the AGN, how the broad components are changing, but also how the continuum is changing. But in the case of the Super-Eddington AGN, since they are not varying so high, we can get a mean spectrum and increase the signal to noise, and also perform a good, very good fits, which can help us with other kind of objectives. And also, aluminum is observed in this redshift range that is a suitable range for making, for example, cosmological analysis. There are some previous fits, automatic fits using these components. However, we decide to repeat the fittings because crucial components, especially for the Super-Eddington AGNs, are not included, like the Fe3 or the Fe2. If we are not included these components, the carbon tree is taking the relevance of this line. Here we have a strong contribution of the Fe3 that is coming from the Lyman alpha fluorescence. So if we are not including here the Fe3, the carbon tree is overestimated, and we will get a ground measurement. So that's why it was really important to repeat the fittings, and we are doing again using an automatic code. So it is really permit us to analyze samples, a large number of samples. So we have identified in our small samples that if we take this flux radius, basically if we are able to measure the aluminum, the silicon, silicon and also the carbon. So that's why it's very important to measure the carbon and constrain very well these emission lines. So we will get that using only this flux radio, we can constrain and we can get an indication of where are the Super-Eddington AGNs. So if we correlate this flux radio, so basically our Super-Eddington AGNs will be located in this part of the region. These are our results from the automatic fittings. You will see here we have some outliers, but again, they are coming from automatic fitting, so it's not like a fit per object, so we cannot expect that the things are completely perfect. So here it's our results, and these are the behavior of the black hole mass has a function of the redshift. So our SDSS reverberation mapping sources estimate that the black hole mass using the aluminum is here. So you will see that there is really they are not behaving so different from the general AGN population. Especially here I am using the data from the Shen et al. Catalog using the magnesium 2 and also the carbon 4. So you will see that our sources are here. But the most interesting point is that when we correlate, when we use the fundamental planes for the black hole masses, here we realize that really we are not getting Super-Eddington sources. Super-Eddington sources formally that they are accreting close to the value 1. The maximum value that we are reach is around 0.5, 0.6. So this result suggests that really SDSS reverberation mapping samples are not really accreting close to the Eddington limit. At least this sample is biased. We know that it's biased by flux. Probably we need more sources with large value, but well, this is our preliminary results, and in the future will be confirmed. Well, so from our previous samples, we know that the high Eddington sources tend to show high metallicity. As I told you before, here we have a different kind of emission lines that the fluxes of these emission lines, if we correlate, can help us as a metal indicator. So we are using carbon 4, helium 2, silicon 4, and also the aluminum to try to constrain what is happening. So throughout using photoionization codes with the routine cloudy, we can get a constraint of this. Before we get indications that really this Eddington ratio are getting high metallicities for the gas. However, this time our colleague Marcena Sniegowska performed a decomposite of the carbon 4 profile of the broad component and also the blue component, and with the decompositions she can estimate using this flux radio how the metallicity behaves, and you can find the values of the metallicity in this part of in this scale. So you will see that we are really getting super solar values for the Super-Eddington AGNs, but also we are getting an enrichment. Apparently there is an enrichment of the aluminum. And you will see also we are getting denser regions and also really very low ionization parameters. However, in the case of the outflows, really we are not constrained very well the properties, so the properties can be found here and here. So the most important result of this is that the gas of the outflows and the gas of the real components are really different kind of chemical composition, and probably in the virial component we are getting a high chemical composition because there are some hints that there is a starboard rings in the high Eddington AGN, and that's why this zone is enriched by these elements. Other of the things that we can do it with the Super-Eddington AGN is use as a standard candle. But a standard candle is a source that we can determine the flux or the luminosity independent of redshift, and it is quite crucial for cosmology because if we can determine the distance to the source observing one parameter for one object, for example supernovae or Cepheids, we can estimate the distance, and then we can make cosmological analysis. So in the AGNs it's quite crucial to identify identify a property that behaves as a standard candle, but we know that if the ratio black hole mass and Eddington ratio is constant, and we can get that basically if this ratio is constant, we can consider AGN as standard candles, and it will be happening only in the Super-Eddington AGNs when the value is close to 1. So if we take this consideration, so we will get that the luminosity will be a function of the full width of the line, and this relation, at least this exponent, is really similar and remember us to the Tully-Fisher relation. So if we get this, so we are able, of course, here we have to apply a correction because the width of the line is really affected by this. But if we apply this, so we will get that we can get the luminosity only knowing the width of the line, right? So if we plot here our SDSS data that are the stars, so you will see that here they are close to the standard lambda CDN model, that is the black line. And we are comparing with others of our previous Super-Eddington samples. However, you will see that our sample is at the top of this relation, so something is happened. So there are some questions here if really, first, we are not taking the constraint that we are getting only consider our criteria. We are not getting really extreme XA Super-Eddington. It means volume close to 1, so probably that's why some our sources are here or they show a kind of departure. Also, we have to check the automatic fittings because the previous samples well done source by source the analysis. However, now we are doing automatic fittings and we have to know exactly what is happening and why it's not very well reproduced here. And also is the question that probably is the solution, but also we have to confirm with other kind of analysis. I'm now working on that. If really our sources are not close to 1, that it probably can be the scenario, and probably that's why. So before to use this SDSS sample with cosmology and the analysis that I'm proposing now, so we have to consider this before to make this sample with cosmology. So this is my summary, and basically we can use Super-Eddington AGNs are easy to identify in large samples, only observing the spectroscopic properties. Aluminium 3, at least for the results that we have, can be used as a medial estimator. However, we need F-beta measurements to confirm these results. We are not finding with these results that SDSS reverberation mapping sample include a Super-Eddington AGNs here. Close, it means radiating close to 1 or upper, with upper values. However, it suggests that probably this is SDSS reverberation mapping is affected by bias, flux bias. So probably also we will need to increase the flux of this sample, or include other kind of sources to increase the luminosity and then to reach the Eddington ratio close to 1. But also it could be a challenge for the reverberation mapping, because for long monitoring programs we will need long monitoring programs that we will take like years, 4 years. It has been showing that it's able to get really very good value, so it's really now a challenge for reverberation mapping. From our previous result with Super-Eddington AGNs, we know that this the broadline region of these sources is denser compared with the general AGN population, and also show large metallicities that probably are associated to a burst of star formation. So please here and go to this last review that we have published when we claim why the star burst is associated with this these high metal regions. And also it's crucial to identify the XA or the Super-Eddington sources for cosmology, because if really are not able to identify Super-Eddington sources, we cannot make cosmology. So my next step for me is the analysis of the new SDSS data using the ACME sample. So let's see in the future we can get some Eddington source here. So thank you very much for listening this talk, and so I will be so happy to get any information, any comment, suggestion, and also collaboration. So you can send me an email here, and I will be happy to reply and keep in contact with you. So thank you very much, and stay healthy.